Hello, good day, and welcome to everybody here. My name is Andrei Shepcic, and together with me there is Simone Meneghin. Today we will be talking about current transformer testing with iCT1. Thank you all for joining us. We will have a PowerPoint presentation, but we also have some nice videos demonstrating how does iCT1 work and how does it test current transformers. But because we will be talking about current transformers today, let us see exactly what are current transformers and how do we, let's get to know the current transformer before we speak about testing of these devices. So a current transformer is an instrument transformer, meaning that it's not a power transformer, is a primary equipment that is used to transform current from high primary value onto a smaller value that can be then used to be sent to secondary equipment like protective relays and energy measurement devices as an information without damaging them. It means that literally current transformer and also the voltage transformer are like eyes and ears for protective relays and energy meters to understand what's happening around them. So you can see here various types of current transformers: high voltage, medium voltage, low voltage, and here you can see the symbol of a current transformer. And I would like also to say as a side note that when we talk about current transformers, we can say that the currents on the left side or on the input or on the high voltage side of a current transformer are called primary values, while the currents on the right side or the output or the low voltage side of the current transformer are called secondary values, referring to the concept of primary and secondary test sets. So for example, the current that runs here will be primary current, the current that runs here will be secondary. The same here, this will be connected to the primary, here you will have the secondary. Primary, secondary. This will be primary and this will be secondary. So when somebody wants to use a secondary test set, it means it will be, let's say, lower currents or voltages, and primary test set will be higher currents and voltages. Moving on, we have one saying in ISA-Altanova which says a transformer does not know what it is. That saying comes from Mr. Primo Lodi. For a long time he was the chief R&D, and Primo wanted to tell us with that to be aware that in general transformer has a primary and a secondary winding, and depending how we connect the source and the output, we can change the functionality of the transformer. It can be, let's say, a step up or a step down transformer. That all depends from your point of view. So let's say that I have a 10-to-1 transformer. That means ideally that 10 volts on the primary side will produce 1 volt on the secondary side. This is something which we learned in school, especially when we were discussing the basics of the transformer, because often transformers are used to step down the voltage, because you have big transformers near big cities which are then stepping down the big voltage, the high voltage, which was used to transmit the power coming from the power plants. So coming back to this topic, but because the power on the input of the current transformer and voltage and power transformer, all these transformers needs to be the same as the power on the output, at the same time the current on the secondary will be 10 times higher than the current on the primary. So if we have a classical school example, input 10 volts and 1 amp, and the ratio 10-to-1, on the secondary side, we will now have 10 times lower voltage, 1 volt, but at the same time, 10 times higher current, because the input power is equal to the output power, meaning that U times I is 10, and it needs to be 10 also here. Of course, in a real transformer, it is a little bit different because there are some losses, but the concept is more or less the same. So the current transformer is just the opposite of the one we see above. So when we talk about CT, what actually defines a CT? What is so special about a CT? Well, a current transformer will actually usually have, not usually, always, will have more turns on the secondary than on the primary side, which would make it reduce the current and increase the voltage. Usually that type of transformer will have one, maybe two turns on the primary side. So it will not be a 10-to-1, but a 1-to-10 transformer. And in this example too, if we have 10 volts in the primary and 10 amps on the primary, and we have 10-to-1 ratio on the secondary, we will now boost the voltage. It will go up to 100 volts, and we will reduce the current, because the sum, not the sum, but if we multiply these two values and if we multiply these two values, we will get the same number, which will be 100. So one might say that CTs are step-up transformers that effectively increase voltage and reduce current proportionally. Having said that, I have to mention now one of the tips and tricks when it comes to CT. You should never leave the secondary side open, because if the secondary side is left open, then the voltage which is induced can damage the insulation of your current transformer. When your current transformer is connected to a relay or an energy meter or power quality meter, its secondary is short-circuited because it is connected to the amperometric input, and this is effectively a short circuit. So that's why we say that the secondary side of a current transformer always needs to be short-circuited or needs to have some kind of burden on it. Moving on, here we see a vectorial representation of what is happening in a CT when it is operational. We see that we have the primary side with its inductance, and then we have the secondary side. Now, on the secondary side, the flux, which is created through a primary winding, creates an electromagnetic force. That electromagnetic force induces these two currents, current 1 and current 2, and this current is the current of losses. So here we have the losses in the core, due to eddy currents and due to magnetization, as you can see. Here we have the losses due to ohmic characteristic of the wires, which effectively means there is a voltage drop because the wire has a finite resistance. And here we have the impedance of the connected relay or energy meter. So what we do, if we draw this in one plane, we can see that we have here the voltage, which we can find here. And then if we add to that voltage, the voltage drop here, we get the electromagnetic force, which is here. And then the angle phi b is between the voltage and the current, which runs through the load, or let's say through the relay. And if we add to that current, this current here, which is lost due to losses in the core, we have a total IP current. So this is how we can represent the functionality of our current transformer. And I forgot to mention, so this current here, as we said, is losses, this is magnetization, and this is due to resistance. And when you sum them up, you get your losses, which are then summed up here. So this is how the vectors move inside of our current transformer. But if we would have a chance to cut our transformer into, let's say, a few pieces, or to take a peek inside, this is what we would see. So this is your typical current transformer, which is used for high voltage purposes. What you see here is that we have a primary terminal, which extends itself onto a primary winding. You see this line, that's a primary winding. And then you have here a core, and then we have a secondary winding. You can see here the secondary winding. Then we have a porcelain insulator, graded insulation system, and here we connect our protective relays or energy meters. This is where we connect with copper wires, which then run all the way to the substation. This is one of your typical examples of a current transformer. This here is another example very similar to this one. Here in this case, we have oil as an insulating medium. That's why we have this top cover to protect everything. And then inside here, you would get oil, and proportionally to how much oil you have inside, that's how much this would raise and show you the amount of oil, since this is oil expansion device. And then we have here the connection of the primary side. This is where we physically connect your line. Then we also have insulation, paper oil insulation, a porcelain insulator, and also high voltage bushing with intermediate screens. And at the end, we have again the box where we connect the secondary side and also the base. So this is what our current transformer looks like theoretically, and this is what it looks like when it is in a substation or freshly produced in a factory. So we see that they both have a top cover. Oil level indicator is not that well seen here, but what we can see is the primary side where we connect our line. You can see the line is connected here, and inside we probably have only one winding. And then we have porcelain insulator, which can also be a silicon insulator. We have the secondary terminal box where we connect the relays and the energy meters, and of course the base. So this is what your high voltage CT would look like. And since we talk about types of CTs, we can see that we have a so-called bar type, like a toroidal type of CT, which is used quite often. It is used quite often, especially because it's made usually for currents greater than 100 amps on the primary side. And we also have a wound primary type for smaller fault currents due to thermal and structural limitations. And we have to also say that when we're talking about current transformer, we need to distinguish two types: metering and protective CTs. In the morning when we were doing our first presentation, I made one example. I took an example of Mad Max in the 80s. In one of the sequels, there was, I hope you guys remember, Master and Master Blaster. So Master and Blaster was like two guys, like one entity. You had a huge person who was fighting and a small person, little person who was being carried by this huge guy. I always perceive transformers, current transformers, metering CTs would be the master and protective CTs would be the blaster, because metering CTs have to be very accurate and have to also protect what they are connected to, while protective CTs are the big guys, are the guys who are always ready to suffer even the greatest currents in the primary side in order to bring the correct information to the relay or to some other device. So the biggest difference between these two would be actually the knee voltage and accuracy. So what do I mean by that? So the knee voltage and the accuracy are two primary differentiators when we talk about metering and protection CTs. So for a metering CT, you have to be very accurate. Metering CTs are used to measure the amount of current which was consumed by the user, and that's why we talk about accuracy levels of 0.1, 0.2, 0.5, maybe 1%. So they're quite accurate. While if we talk about accuracy of current transformer, it's 1, 3, maybe 5%. It's not so accurate. Also, metering CTs above the nominal value, they need to saturate in order to protect the inputs of the instruments under fault conditions. So what do we mean by that? If you have a metering CT connected to your primary circuit, and then the secondary side of that metering CT is connected to a, let's say, energy meter, if there is a fault and you have, let's say, 1000 to 1 CT, and you have 20 times nominal current, you would see 20 times, you would see 20 amps on the secondary side, which would probably burn the sensitive inputs of energy meters. Since we don't want that to happen, we want the measurement CT to saturate as soon as possible. As soon as you go over, let's say 100 or 120%, sometimes more, of nominal value, it needs to always show the same amount of current on the secondary side to protect these devices, but also not to take into account all this current which was being generated, which was being, let's say, used while the fault was being active. So they also often have a very sharp magnetization characteristic, which we will see in the next slide. And metering CTs have up to few volts or a few tens of volts the knee point. So the knee point is not bigger than, let's say, 50 or 70 or maybe 100, because they need to saturate fast. So this is metering CTs. Protection CTs, that's the blaster. That's the big rugged guy. So they need to accurately transform a wide range of currents from nominal to maximum fault currents, which can be 10, 20, or 30 times your nominal current. Why is that? Well, let's say that we have an overcurrent protection and that we have a time inverse characteristic, which means that if the current is big, you will trip very fast, and if the current is low, then you can wait for a long period of time. So you need to know exactly how much the current is. Are we talking about 2 times nominal current or 20 times nominal current? So it needs to always provide accurate information, what it sees on the primary side, in order for the protective relay to understand what's really going on, and in order for this relay to make a good decision when it needs to trip, or how long does it need to wait before it trips. So saturation should be avoided at all costs in order to accurately transform primary to secondary current. The trade-off is accuracy compared to metering CTs, but that's not a problem for a protective CT, because when you have a fault, your current doesn't go up 5 or 10 or 15%. It shoots up 3, 4, 5, 10, 20 times more than your standard nominal current. And that's why 1 to 3 or 5% is not such a big issue in this situation. So the knee point is usually found at few hundreds or few hundred volts or even few kilovolts. So we've been talking about this knee point. So let us see exactly what this knee point is. So we have two definitions. According to ISC 61869, the knee point is defined as the voltage at which 10% increase in applied voltage increases the magnetizing current by 50%. For voltages greater than the knee point, the magnetizing current increases considerably, even for small increments in voltage across the secondary terminals. So this is how IC defines it. IEEE or ANSI have slightly different definition, which says, as you can see here, the intersection of the excitation curve with 45-degree tangent line in the knee point. So here you would have 45-degree, and more or less, even though they have a different definition, I would say that they describe, of course, the same thing. They definitely describe the inflection point in which this straight line stops being a straight line. Basically, the point is this: you want always your CT to function in this region here, where it's proportional, and you don't want it to function here where it's not proportional. So we always want to avoid saturation. And in order to do that, I'll just mention that a transformer, current transformer, it's good if you demagnetize it every once in a while, because you can have your CT working at the edge of your saturation without you knowing that, and it can work fine for years and years to come. But at one point in time, if you have a big current and you expect it to work, it might saturate and send wrong information to your relay. Moving on, this is what we would consider to be a very steep or inflection point. So this would be your magnetizing CT, and this would be your protection CT magnetization. Now, before we continue, also let us talk about the concepts of ALF and ISF, because we will see that later on. ALF is something which is used for protective CTs. ALF is accuracy limiting factor, which is used to describe how, let me put it like this, robust your CT is. And let us read this. In order to maintain the accuracy of the CT during a fault, you should be able to accurately show on the secondary what is happening on the primary side, even if your current on the primary side is 10, 20, or 30 times the nominal current. So the best way to explain this would be using an example. Here we have example 1 where ALF is 10. So when you see a CT, you will always see, and if it's a protective CT, you will see something like 5P10 or 10P30 or 5P20. Let me explain what this means. P stands for protection, and 5 stands for percentage, and 10 is this. It says if your current, nominal current on the primary side, is 10 times bigger than the nominal current, at that point the accuracy cannot be worse than 5%. While in this case, if your nominal current on the primary side is 30 times bigger than the nominal current, then the error cannot be more than 10%. So if you have 1,000 to 1 CT and you have, let's say, 30 kilovolts running in the primary side, you shouldn't have a value on the secondary side which is much different than 30.3 amps. So this is also, I mean, we say that there is a trade-off between the metering and the protective CTs when it comes to accuracy. And of course, metering CTs are more accurate, but that does not mean that the protection CTs are inaccurate. They're just not that accurate as metering CTs. Another parameter.
Andrei, sorry?
Yes, please.
May
Simone.
I add one detail?
Sure, feel free.
Go back to the previous slide.
Sure.
When we say that the current can reach 10 times or 30 times the nominal value to guarantee the accuracy, let's say 5% or 10%, this means that the burden to be connected to the secondary side must be the nominal one. I mean, the burden that absorbs the full power at the nominal current. In different conditions, the ALF may be different.
Yes, thank you for reminding me. That is quite important, because sometimes we forget that the CT is actually functioning in an environment where you have a primary side, the secondary side, and then you have something connected to the secondary side. You have the wires, and then you have your relay, or maybe few relays, and that's the burden. And the burden also very much dictates the behavior of your CT. That's why every CT comes with the maximum allowed burden. Thank you, Simone, for reminding me. The next thing we will be talking about is ISF or FS. That is defined for a metering CT. So instrument safety factor, metering CTs have to protect sensitive inputs. We said that, of energy meters, and they are connected to. That is why they need to saturate soon after 100% of nominal current on the primary side is reached. So ISF is the ratio of instrument limit primary current. We will explain what that is. Actually, it's saturation current to the rated primary current. And what is the instrument limit primary current? Well, the instrument limit primary current of metering CT is the value that the primary current beyond which CT core becomes saturated. So if we have, again, 1,000 to 1 CT, which is a measuring CT, if we reach, let's say, 1,100, and we see on the secondary side 1.1 amp, and then we go to 2,000 amps on the primary, and we still see 1.1 amp on the secondary side, that means we have that means that 1,100 is the ratio, is the instrument limit primary current. So here the example is, if ISF is 5, that means that CT will saturate when primary current is 5 times nominal current. Now, since we explained the basics of the CT, I hope that is clear for you. We didn't go too much in depth because the CT is actually pretty straightforward device, but still we have to keep in mind that the CT doesn't stand for itself. I mean, it is connected in the system to a burden and to the primary side. Now we come to iCT1, which is fully automatic current and voltage transformer test set with integrated switch box. That means that with one box you have here, you can you can test a whole CT with only one set of connections. You don't have to change connections every once in a while, or heaven forbid, you don't have to buy additional accessories if you wanted to test a multi-tap CT. And let's be honest, most of the CTs are multi-tap CTs. So you have an integrated switch box. And let me give you some finer details, finer points regarding the iCT1. So it's designed to test current, voltage, and combined transformers. Also, time saving, meaning that one setup of connection is done to perform all the tests. The main tests which this device performs is ratio R, ratio and phase error, excitation curve, or the knee point test or magnetization curve, winding resistance, accuracy, burden, and so on. We have an integrated 6 steps switch box able to test CT with saturation voltage up to 2 kilovolts and up to 30 kilovolts applying DC indirect method. So let me stop here and explain what that is. We have 2 versions of iCT1, the standard and the advanced one. Both of them can generate AC voltage up to 2 kilovolts in nominal frequency, 50 or 60 hertz. So you truly get your 2 kilovolts to test your knee point. But if the knee point is higher than that, then we apply different method. We model our CT in a certain way using our patented method, and we saturate the core using a DC voltage, and that way we can test the knee point of CTs whose knee point is as high as 30 kilovolts. We will see later which type of CTs have such a high knee point. Also, we have an integrated demagnetizer, which is important because I mentioned before, there are situations in which especially some differential protections did not trip or tripped wrongly because the transformer, the CT, was already close to its saturation point, and then the huge current came and the CT saturated. So this would be like, let us call it not a mental hygiene, but demagnetization hygiene of your current CT. So every time you test a CT, it's a good idea to demagnetize it. And we also have something which we call the CT Explorer function. It is able to find the nameplate data of the CT. If you don't have any nameplate, you can connect, just press start button, and then watch the magic unravel in front of your eyes. The device itself is compact and lightweight. So the dimensions are 41 centimeters high, 34 centimeters width, and 205 centimeters depth, and 16 kilos. And I haven't added this because I didn't want to sound as a salesman, but the fact is that this is really a moderately priced test set. So the best way to find that out is to ask for a quotation, but it is really not as expensive as some of the devices we see in the market. So without any further ado, iCT1, which uses Wi-Fi to communicate with your test set, with your PC. But actually, that is not necessary, especially if you are using your iCT1 by simply interfacing with it using a touchscreen display. So we have a 7-inch touchscreen display, which is actually used as an interface between you and the device. Wi-Fi will be used to transfer data, or of course you can use the software if you want to be further away. Of course, also we have, as we mentioned before, 6 terminals integrated switch box, and if you don't want to use Wi-Fi, we use Ethernet and USB port. On a USB port, what you can do, you can simply put in your USB key, and in doing so, you can then transfer the data onto a USB key, or from a USB key onto your iCT1, you can transfer some predefined tests or test plans. Rugged case with handle goes without saying. We know that this will be, let's say, used in environments where being gentle is not something you see every day. So you get a sturdy, rugged device, which is then ready for you to operate it. The device itself can test current transformers, voltage transformers, and combined transformers. And let us list the tests which it can do. So it can do a turn ratio and polarity in voltage mode, burden secondary side, excitation curve standard method 2 kV, excitation curve DC method can be done only by advanced version, and that's basically the biggest difference between advanced and standard. Winding or burden resistance we can measure, and when we measure this is very fast. This is one of the nicest things we have done recently, I would say, because winding resistance can sometimes be slightly longer, let's say 30 seconds, 1 minute, sometimes hopefully not longer than that. But with our pure DC output, this is a piece of cake, and you can test your resistance very fast. And then you can also test no load current. You can do an accuracy test, demagnetizer, and CT Explorer. And as you can see here, we respect or abide to all international standards, the old IC 644-1257 and the new one 61869, as well as IEEE or ANSI C57.13.1. We haven't talked about VTs today because the star of the show is CT, but with the same device, let me just mention, you can also do the ratio test of a VT or a ratio of electronic VTs or no load current or even accuracy of the VTs. So you get not double functionality, but you get altogether about 15 functions in one device. So one device to fully test your CTs and VTs. And just to close this part, so the biggest difference between standard and advanced version of iCT1 is excitation curve using DC method. So why is this test needed? Well, it is needed for CTs that have the knee point above 2 kilovolts. In practice, those would be CTs on 230 kilovolt and 600 kilovolt or higher voltage levels, because simply these CTs are made in such a way that they have a very big magnetic core, and the saturation comes much after, let's say, only 2 kilovolts. So we are more or less at half of our presentation, in the middle of our presentation, and I would like to see if you guys have followed, guys and girls, and I would like to ask you a question. So a short poll. Let me ask you, talking about some advanced communication feature iCT1 uses: A, Bluetooth, B, Wi-Fi, or C, Bluetooth and Wi-Fi and smoke signals? So let's see, how will you answer these questions? This question, I'm happy to see that already 37% of people have voted and 89% of attendees have given a correct answer, which makes me feel good because I understand that you are really listening to what we're saying. I see that already 40%, 41% of people have voted and 85% have the correct answer. So we'll give a few more seconds to everybody to cast in their votes, and then we will close the poll. So let us close the poll in 5, 4, 3, 2, 1. And the correct answer was B, Wi-Fi. And let us share the result. So 86% of you have answered Wi-Fi. Thank you for that, and thank you for listening. Now let's see the results and continue with the presentation. So luckily, now I might be talking a little bit less because soon we will be showing some videos on how the iCT1 functions. But before we do that, we will say that iCT1 houses one main generator, which can provide us with high AC voltage, low AC current, low DC current, low AC voltage, and low voltage for excitation curve for DC method. High AC voltage will be used, of course, for the knee point test, and we can generate up to 2 kilovolts and 1 amp for about 5 seconds. We can generate, 2 kilovolts with lower current for more than 2 minutes, and the maximum current in high AC voltage output is 15 amps actually, and we can generate that for more than 120 seconds. Low DC current will be used to measure your winding resistance, so 6 amp is maximum, 30 volts, and the maximum power of 180 watt. Low AC current will be used to test, let's say, your well, you can use it to test your burden or something else, but usually for burden we use voltage. The maximum is 6 amps DC and 100 volts AC, and the maximum power is 200 VAs. Low DC voltage for excitation curve up to 30 kilovolts. We can generate up to 200 volts DC. Maximum output power would be 2 amps RMS, and the power in the case of US, let's say, would be 330 VAs, because in US we have 110 volts coming from the socket. All the outputs are electronically protected. The frequency goes from 15 Hertz to 400 Hertz, and the resolution is very good, which is 10 millihertz. Another thing which is very important to emphasize here is a very high accuracy when it comes to measurement. And trust us, this is one of the beautiful parts of the device, because it is not easy to measure with such a high accuracy. And you can see here that we are mostly, when we talk about typical error, we talk about, let's say, between 0.02 and 0.025. Guaranteed is 0.05. You cannot guarantee something that accurate when you are in an environment which is inherently full of noise, and that's a substation or a power plant. So very, very high accuracies for the AC current, DC current, AC voltage primary and secondary side. This would be the measurement, and the DC voltage. So then we have, let's say, the measurement of complex values, which by complex values I mean ratio measurement. For ratio measurement, we have to be accurate in generating voltage and in measuring voltage. Actually, if I haven't mentioned it, how we do a test, what we actually do, we generate on the secondary side the voltage, high voltage, and we measure on the primary side. If you have a 1000 to 1 CT, and if we generate, let's say, 1000 volts, which we don't, we usually generate much less, but let's say, just for the sake, 1000 volts on the secondary side, we will be measuring 1 volt on the primary side. And you need to measure that with the accuracy of 0.025, for example. So this is really, really accurate device. And you can see that the accuracy of ratio is between, let's say, 0.02 and 0.05 for the range between 0.8 and 2000. And for higher ranges, it is a little bit lower, but still very good accuracy. For VT ratio measurement, again, we are between 0.03 and 0.2, and slightly less for higher rates. And in burden measurement, also, we have a very high accuracy. So you can see that the accuracy is between 0.1 and 0.2%. Winding resistance, which uses a pure DC source, has fantastic resolution of 0.1 milliohms and the typical accuracy of 0.05%, and the guaranteed accuracy, which is twice, so 0.1% plus 1 milliohm, which is really, really very good value. Phase angle measurement, of course, here what we see is that we need to go from 0 to 330 degrees. We actually need to measure the angle between two values, whether is it 2 voltages or voltage and a current or 2 currents. And we see that the resolution is 0.01 degrees, so less than 1 minute. And this is the resolution, and the accuracy for a cos phi between 0.8 and 1 is between 2 and 4 minutes. So which is more than enough for, let's say, your standard CT, which we use in a substation or a power plant. The applications for such an instrument can be factory testing and also commissioning. because it's easy to use, it has a high accuracy, and it is also very fast in doing the tests. So without any further ado, I give you the main screen of iCT1. So iCT1, when you started, you use your 7-inch touch screen to press here or here to test current or voltage transformers, or of course you can use this device as a simple source or a device which measures something. So control and measurement is also an option. You can use them, not within an application. File manager allows us to save results and to open the saved results, and the settings of course allows us to set some values, time, date, nominal frequency, etc., etc. When you want to define a header, you also need to say how many cores are there. Is there only one core, or maybe two cores, or maybe three cores, and how many taps every core has. So you can have a CT 3200 to 1, which has two cores. One core is protection, the other core is measurement, and we have, let's say, 4 taps on the protection core and 2 taps on the measurement core, and that's fully doable. So right now, I would like to show you the first video, which shows us actually how Matteo, my colleague who made these videos, is defining a header of a CT. So let us start. So here first we will say what's the name of the substation. Of course, you can fill this in completely. Then we go to the second part where we define what is the nominal secondary current, which standard, what is the nominal frequency, 50 or 60, how many primary windings we have, and how many cores we have. Here we define, apart from cores, how many taps do we have. And here we define whether the taps or whether the core is metering or protection, what is the accuracy class, and what is the ALF. So we define 5P20 CT. Here, Matteo defined that this protective core has 4 taps, which are 75 to 1, 150 to 1, 300 to 1, and 600 to 1. And here he's showing us how you can define a certain tap. So the name, what is the primary current, rated burden, the cos phi, operating burden, and operating cos phi. This is just to show how the actual change can be done. Here we see a part with all the tolerances, because in the end, according to the tolerances and the obtained value, you will receive a pass or a fail. So for ratio, polarity, so for example, here polarity is 15 degrees. If it's between less than 15 degrees, then you get okay. The ratio is okay. If the error is low, then percentage of that class error, etc. And then we can go back. And just for a second, we can take a look. Just a minute. We can see all the tests which can be done. So header, turn ratio and polarity using voltage method, winding resistance, excitation curve, accuracy, burden secondary side, ALF, ISF, demagnetizer, CT explorer, leakage current, measurement, and all that for just a handful of dollars. No, I'm joking. This was the first video. Now the second video will show us something else. The second video will show us how do we actually do a turn ratio and polarity test. So here we can see one example, which is not the same one that we will be showing in the film later. So we have 800 to 5, 400 to 5, 200 to 5, and 100 to 5 taps. This is the nominal here is 150, the actual is 151. Then 400 is nominal, 75 would be nominal ratio, we have 75.9. Here 40 would be nominal, and we have 38. Here 20, we have 19, and we see that the error is not small, but this is because this is our demonstrational CT. It's not a real CT. We see what is the phase shift here. We see, is it okay? We see we actually generated 55 volts on the secondary side, and this is what we measured on the primary side, and this is the current that we measured. So in order to show you how this test is done, and I hope this will explain a few things. I wanted to stop the video here just to emphasize that always by pressing the question mark button, you will see the connection scheme. And the connection scheme is actually more or less always the same. What we see here is that we connect to the secondary side and we measure from the primary side. Because we want to have a high accuracy, we also connect the shield of the cables. Cables come together with the device. And what we do here is we actually connect, we generate between this and this connector on the secondary side. And then this is transformed onto a primary side, measured, and so on. So right now, we chose that the testing voltage will be 20 volts. This is the voltage which will be generated on the secondary side. Of course, the test frequency can be changed. It can also be 60 Hertz. And right now, we started the test. Let me just tell you that in this case, you will see that it takes a little bit longer to do this. That is my error, because we made this video, let's say about a month ago, when we still had an old firmware. This is now surpassed, and this test would last 50% of the time which you see right now. But we already did the test for 600 to 1 and for 300 to 1. Then we'll also do it for 150 to 1 and 100 to 1, after which we will see all results. Okay, this one is done. And remember, in the end, we want to see all this green and with thumbs up. That way we know that the results are within tolerances. So we can see, for example, for 150 to 1, that we have a very high accuracy of 0.127. And now we are seeing that also the last measurement is very accurate. What you can see here below are intertap results. So right now, let us comment on this result. So we see that the error is very small, between 0.18 and 0.12. We see that the polarity is okay with a very small phase shift. This was the measured primary value, and this was the of voltage and current, and this was the secondary value. And we see that all this is a pass. So this is how we would do CT ratio and polarity with iCT1. Moving on, the next test would be an excitation curve. For excitation curve, I will run the next presentation, the next video. So here you see that we already did this test. Now we're going to do another test. Once again, the connection is as it was before. So what's happening right now is that we first need to actually demagnetize the CT in order to be sure that we have a clean slate when we are doing this test. So you don't see how we are increasing the voltage, but you will see how we decrease the voltage, how the device decreases the voltage. And the good thing about this is that we will actually do only one knee point, only one saturation curve, and all other saturation curves will be calculated from that saturation curve because they are all on the same core. This is essentially a test of the core, and the number of turns on the secondary side does not influence the form of our curve. So we can see the curve, the first curve, IS1, IS5, and soon when the test is done, we'll be able to see all other curves. Later, you can also check all the results in a table test, which would show you the exact values, what was generated, and what voltage was generated, and what current have we measured. So right now, we're concluding the first test, and in just a few seconds, we will have the result for all our taps. Let me go back just a second. So what we see here is the curve for 1S1, but also 1S4, 1S3, and 1S2. You can see that here. And then we're also going to show the table test, which means all the values of current and voltage, which were voltage which was generated and current which was measured for each tap and also for intertaps. So this is how we do the excitation curve. I will just turn your attention to the fact that we already have two tests here, which effectively creates what we call a test plan. Moving on, excitation curve for transformers for CTs which have a let's say knee point above 2 kilovolts. We use the DC method because it is an easier method. So what we do is we model the magnetic core in a certain way, and if we do a test like this, we don't have to bring a high voltage source. We don't have to be very much afraid of burning something with, let's say, not professionally handling the test set. So we are not working with very high voltages. We are working with the voltages up to 150 volts DC. Absolute maximum is 200, and it is a lighter and faster way to do a test. So it is our patented method in which with the DC current, with the DC voltage, we saturate the core, and then through a series of mathematical calculations using modeling, we calculate the knee point. Then the next function will be the CT Explorer. So if we have a situation in which we don't know what are the nominal values, in that case, we connect our iCT1 and we press start. We wait for about a few minutes, 2 minutes, 3 minutes, and we get our result, and we automatically, the nominal values of the CTs are filled in. For this function, regretfully, I don't have any example, but I go for the next one, which is accuracy test. So accuracy test is, of course, very important test, especially for metering CTs. We have different classes, accuracy classes, so 0.1, 0.2, 0.5, and this means that when you are generating 100% of nominal current, you need to have maximum error of 0.1 for 0.1 class, 0.2 for 0.2 class, and so on and so on. So what we do with our device, we simulate different loads, because the loads, according to IEC 61869, had to be 5, 20, 100, and 120. Of course, a user can choose any load he wants, and then we also do the verification not just of ratio but also of phase displacement. This would be for measuring CTs, this would be for your protection CTs, which often have accuracy which is slightly lower than your metering CTs. And if you want to do an accuracy test for a metering core, it will look something like this. As we said, 5, 20, 100 and 120%. And here we see the results. And this will be for our protective. If we want, I have also a short film showing us how we test accuracy. So accuracy is tested like this. Again, showing the nominal values. Just to mention, when we are testing accuracy, winding resistance and also burden is an important factor. So we can see here we are showing what are the nominal values. We see that the accuracy class is 0.5. And after we have performed winding resistance, we will take this result into account when we will be doing accuracy test. So let's start. We can choose which points we want to do, but what Matteo is first doing, he is choosing the compensated winding resistance and the operating burden as his parameters while doing this. And in this case, he's just showing you that we can remove some points or add some points. Actually, later we will do a test just at 100% of your nominal value. And right now, he's going to choose 100%. He'll press start. You see that the test is in progress. It's written here. You have a little sign showing you to be careful, not to approach the device maybe if you're doing the test if the voltage is high. And right now the device is evaluating the load, the flux. It is generating 100% of load, let's say, simulating like it is generating, like it's giving maximum power, and soon we'll see the result. So now we see the result, and we have here 18.4 millipercents, so 0.018% of error for this CT, which is very good, and 0.365% of minute when it comes to phase shift error, which is a very, very good result. This would be our CT accuracy. And then the last single test, which I wanted to show you, but definitely not the least, is winding resistance. So winding resistance is one of my favorite tests because we can show how powerful our device is. So what we do, we have maximum 6 amps DC. And with this 6 amps pure DC, what we do is we measure resistance. So let's do it. Again, the connection. We'll change this to 2 amps. And we will measure. We will also decide whether we want to have a temperature compensation, what the material, is it copper or aluminum. And now we will quickly, very quickly, do winding resistance for all 4 taps. So we have 600 to 1, 300 to 1, 150 to 1, and 100 to 1. And we're seeing a coherent results because for the secondary side, for 600 to 1, we have 2.6 ohm, and for 300 to 1, we have half of that, 1.37, and then we have 150 to 1, which is half of this, and this is 100 to 1, which is not the half of this, but it is, let's say, 2/3 of this. And actually, in less than a minute, you have tested all 4 cores. So this is This is the winding resistance test. And let's move on and mention also one important thing, which is a test plan. So for a test plan, I'm going to show it to you, but I might fast forward a little bit because we will be doing 4 tests. I don't want too much of your time to be wasted. So the point of test plan is you can prepare in your office before you go to the site all the tests you want to do on CTs, especially if you have nominal values. That's great. And then when we prepare this in the office and when we run it, we can save this file and always use that same file to test that same CT. So let us take a look how this looks like. So no, this is accuracy test plan, and let's see what did Matteo chose this time. So we will have turn ratio and polarity. Then we will do an excitation curve test, after which we'll do the accuracy test for just 100%, after which we will do winding resistance. And we will press start. So you can see the first test is ratio and polarity for 300 to 1. You see here below test plan, step 1 out of 4. And let me fast forward a little bit this. So we already saw a value of almost 300 to 1, but we'll wait to get a final. So this is now 297 instead of 300, and we have an error of 0.87 or 88. So now the next test will be executed. Now we're starting the excitation curve test. Here below, we always see the explanation what's happening. I'm going to fast forward a little bit to get results a little bit faster. After this test, we will see the accuracy and then the winding resistance. So it's the curve coming down. And we see here the knee point, which was measured. So the knee point is at 63 volts. And this would be the accuracy test. For the accuracy, we expect to have good accuracy here. Right. And I think we have our results. So 0.55 and 6% of a minute. This is the accuracy of the device. And the last one would be, of course, winding resistance, which would be the fastest one, which is the sentence which I never thought I would say, but it definitely is the fastest one. So we will generate 1 amp and we will measure 0.78. And with that, in 3 minutes and 23 seconds, we have fully tested our CT. Of course, we have some greens, some yellows, which means this is fully okay. This is not okay, meaning some parameters are okay, some parameters are not. The idea with a test plan, which you can create in your office, you can do everything much faster. So before we finish, I'll also show you the software, a fantastic software created by our colleague Stefania, which allows you to prepare the tests and also print the results. The results can be printed in different forms like PDF, doc, docx, XLS, XLSX, etc., etc. And with this, we finish the presentation. Thank you very much for your attention. And before we actually finish, I would like to ask you a second question to see if you've been following what I was saying. So the question is, in order to measure a knee point of CTs with knee point above 2 kilovolt, iCT1 uses A, AC modeling coupled with sweep technology, B, DC voltage, or C, AC-DC modeling coupled with PD or partial discharge. So let's see, what do you guys say? And after we finish with this, we're going to take some questions. I need to thank Simone because he was very diligent in answering all these questions. If there is a situation, if you cannot vote, if you have some issues with the connection, then feel free to cast your vote in the question section. Okay, I see already 40% of participants have voted. Let's keep it for a little bit longer, for about 10 more seconds. I see that 76% have got it right. And we're going to close the poll in 5, 4, 3, 2, 1. The poll is closed. And the results are, the correct answer is B, DC voltage. 71% of you got it right. Thank you for following closely. Now I'm going to hide the results. And what I'm going to do, let us open the questions section in order to understand what are the questions we need to answer. But before that, let me just show you the last slide. If you guys need to contact your local distributor, just go to www.altanova-group.com and find your regional ISA office, or you find your distributor. Also, I would like to say that if you go on the same website to the Academy part, you will be able to see what will be our next webinars. But now I think it's time to include my colleague Simone